Welcome everyone at this webinar of the Illicit Trade Group. My name is Pim Geelhoed. I'm Associate Professor of Criminal Law and one of the coordinators of the Illicit Trade Group together with Francesco Giumelli. And today we're having a webinar with the title A Data-Driven Approach for the Detection of Illicit Accounts on the Ethereum blockchain. And with us is George Azzopardi. Welcome, George.
Thank you.
George is assistant professor, tenure track of computer science at the University of Groningen. He also is affiliated with the University of Malta, and he's the chief AI scientist at the company Ellul. And he is speaking to us today on this topic related to an article that he published together with two colleagues that's on the screen right now, called Detection of Illicit Accounts over the Ethereum blockchain in the journal Expert Systems with Applications. And that's a very interesting topic from all kinds of perspectives. I guess primarily from the computer science perspective, because that's what his background is. But also, if I try to relate to it, it's very relevant for law enforcement, for enforcement of money laundering, which is, of course, hotly debated in that respect. Money laundering with the use of cryptocurrencies is a very important topic. And they found some interesting things, and George is going to explain all of that. We welcome him, and we're very happy that he joins us, that he is willing to take time to discuss these matters within the ITG group in this webinar. I have to make an announcement that this presentation is recorded. The discussion afterwards is not recorded. So that's so we all know that. And I would say, George, over to you. The floor is yours.
Thank you very much, Pim. Hello, everyone. Good afternoon. Thanks for this kind introduction, and thanks for inviting me to give this webinar today. And other times we would have been in person and in the same room, but this is the best we can do given the circumstances. Last September, I had the pleasure to meet Professor Francesco Giumelli. Actually, we never met in person as well. We only met online so far. And thanks to him, I've been introduced to this community of illicit trade. And since then, we kept regular contact. And now I'm also happy to be even a member of this community. So, yeah, as you said, my name is George Azzopardi, and I'm assistant professor in a tenure track, not tenure tracked yet, still tracking, at the Bernoulli Institute within the Information Systems Research Group. However, my background and research interests are in the fields of data science that deals with structured and unstructured data, such as images, videos, and other types of data, as we will see today. Today, I'm going to give a talk about, to demonstrate how data science can actually be used in the field also of illicit trade. In particular, I will show how we can build a computational model to detect illicit accounts over a blockchain, specifically on the Ethereum blockchain. This talk is based on this paper that I share with you here, which has been co-authored with two other co-patriots. Actually, this is the only paper I have where all the authors are from Malta. Stephen came to Groningen 2 or 3 years ago to read his master's here. And we arranged a project together with my collaborator in Malta, Joshua Ellul, who is the director of the Center for Distributed Ledger Technologies at the University of Malta. All right, so here we have the agenda for today. I'm going to start with some background on what trading and blockchain is, first of all, before we move on to the method that we propose for this problem. After that, I present the results that we achieved and give some insight that we obtained by this study on the most important features. And eventually, we conclude with some recommended future work and potential stakeholders. Okay, so let's kick off with some background. Digital transactions and blockchain. Well, you're all familiar, of course, with the digital economy, which involves trusted authorities such as retail banks, central banks, and hence governments. The structure forces us to trust that our transactions are being processed properly by such authorities, and also we have to trust that they do it with respect to security and privacy. These authorities have therefore access to determine the owners because, well, they input the data of the owners of the account, so they have access to all the information. And therefore they can use this information to fight illegal activity. Okay, then there comes blockchain, which has been a disruptive technology in various industries, also including the digital economy. So what is blockchain? Well, blockchain is a technology that allows transactions, any type of transactions, including financial transactions, but by bypassing third parties. So any person can transfer money to any other person without involving a bank or any other authority. This technology allowed the creation of what we know nowadays as cryptocurrencies. I'm sure everybody is familiar by now with Bitcoin and other cryptocurrencies. So what made blockchain so popular? Made it so popular? Well, essentially, blockchain is a distributed ledger system, which is also public. And as I said earlier, it doesn't need a third party. So this means that on a technical level, any person with a wallet, like a virtual account on a blockchain, can make a transaction to any other person without involving a bank. The ledger is public, so everybody can have a copy of that ledger, but the account holders are anonymous, or pseudo-anonymous, actually. We call it pseudo-anonymous because if at some point the name of a user behind an account address is revealed, then all the past transactions will be associated with that user. One of the most important features in blockchain is what is known as immutability. This means that once a transaction is verified and completed, then it can never be changed or removed. It will stay on the blockchain forever. This is implemented with the use of cryptographic hash functions that are computing from the content of the transactions. Well, in theory, if there is an individual or a group of individuals who may gain access to the majority control of the network, of more than 50% of the network, in theory they can do changes, but in practice this is impractical. So the immutability, anonymization, and the fact that we can bypass third parties, that we don't even need them, have made blockchain very attractive for cryptocurrencies because they have instilled end users, with a sense of trust, especially the anonymization aspect. Okay, here we have the benefits of blockchain. I think I already mentioned them, but there is one more thing. The first one, which is known as smart contracts. Well, we all know about Bitcoin, which was the first cryptocurrency and which popularized also blockchain. But Bitcoin doesn't have the functionality of smart contracts. It was Ethereum actually that introduced this functionality. A smart contract is a program that is used to implement some business logic. And what is also interesting about smart contracts is that they are also immutable. So once they are deployed on the blockchain, nobody can change them as well. And yes, I already mentioned that it facilitates direct transactions between any two parties in a trustworthy and secure manner, as there are no third parties involved. And the last point is that all data is stored in the form of an immutable database. Okay, Ethereum. Well, as I said, while Bitcoin is the most famous blockchain, which started in 2009, Other blockchains have popped up since then, and Ethereum has become the second most popular blockchain, and also its cryptocurrency Ether. Bitcoin only serves one function, it is only a store of value. But then Ethereum, which was introduced in 2015, it was inspired by Bitcoin. Well, all cryptocurrencies essentially were inspired by Bitcoin, but it upgraded upon Bitcoin with the addition of smart contracts. And this introduced sufficient flexibility that gives its blockchain network limitless potential. Okay, let's see some properties about Ethereum now. So we have the Ethereum state, which is composed of objects, or as better known as accounts, externally owned accounts and contract accounts. I will explain this in the coming slide. Then we have the state transitions, which include the validity and structure of transactions. A transaction can have a digital currency of value or other information, because blockchains are not only used for cryptocurrencies, but they can be used for other purposes in logistics and supply chain, etc. So in those type of transactions, we do not have a currency value, but we have other information. And they also include a transaction-related fee in terms of gas. It also uses a sophisticated data structure known as the Merkle-Patricia tree to store all the key value pairs in the Ethereum. A key value pair is the public address of an account and its balance. But without going into the technical details, I simply say that this data structure enables us to verify the data integrity, even when we do not have access to the full blockchain state, if we want to use a thin client, for example, on our machines. Okay, some information about the types of accounts that we can find on Ethereum. I already mentioned we can have what are known as externally owned accounts or contract accounts. Well, externally owned accounts in Ethereum are the identifiers with which a user can interact with the system. We can consider them as the traditional accounts that we open in banks, but you open such an account on the Ethereum. However, unlike a traditional system in which accounts are created by a central authority and have the facility to check for clashes in the identifiers, this cannot be done in Ethereum, as we do not have a central authority. We need a way in which identifiers can be generated in a decentralized way. Externally owned account is nothing more than a public-private keeper. Then we have contracts or smart contracts, as are also known, and these are the identifiers to the code that is running on the blockchain. Then each account has these four main properties. There is the Ether balance, which is the value in terms of the currency Ether. Nonce is the number of transactions sent by that account. The contract code hash relates only to contract type of accounts, and it is the identifier to where the code is running. And storage is the identifier to the storage of the account in the Merkle-Patricia tree. Okay, so you might ask, from all these cryptocurrencies or blockchains, why did we choose Ethereum to focus on the study? Well, as I mentioned, it is the second largest cryptocurrency market, and it has the largest number of active developers. This is something which attracted us also a lot. Their platform is very powerful. It is the most used platform as far as we know, and it was a leader, it still is, in the smart contract platform. And yeah, so these were the reasons why we focused on Ethereum, but what I'm going to show you today can actually be applied on any type of blockchain. Okay, let's have a look at the legal digital activities now. You probably know more than me, so I will skim through them. So yeah, I'm sure these terms are very familiar with everyone in the audience. So I don't think we need to spend too much time on this. We know that money laundering is a big deal, which is the process of changing large amounts of money obtained from crimes, essentially such as drug and human trafficking, into a legitimate source. We're also used nowadays to receiving emails, phishing scams and frauds, whereby with social engineering, people try to steal your identity and therefore have access to your financial details. In fact, this has been a topic of interest for many big banks that have invested heavily in implementing anomaly detection systems. For instance, I have a credit card account with a Maltese bank, and sometimes when I do an irregular, let's call it irregular transaction, spending something not usual from my spending behavior, they call me sometimes or sending me SMSs to verify that that transaction really originated from my side. Okay, here are some facts about economic crime. This was an interesting fact that we discovered in 2019. $29 billion in credit card fraud. It's unbelievable. And apparently it has been increasing heavily during the COVID pandemic. Okay, as you can imagine, same or similar crimes are also going on in the cryptocurrency market. So we need similar mechanisms to be able to detect such illegal behavior. So here are some types of illegal activity that have been discovered on the Ethereum. Well, probably the most popular one is the smart contract Ponzi schemes. Well, essentially, a Ponzi scheme is a form of fraud where a con artist creates the illusion of a legitimate, profitable product or service and promises, high returns for little risk. So this artist then pays the earlier investors from new investors, and they therefore require a constant flow of new money to survive. And then when it becomes hard to recruit new investors, or when large numbers of existing investors want to cash out, these schemes tend to collapse completely. And as a result, of course, most investors end up losing all their money. All right, here's an example from the internet. Again, I'm sure that you also receive such notifications on Twitter and emails, you name it. So yeah, be careful how to react to such notifications. Okay, next topic, reviewing transactions and big data. So how are banks dealing with this? It is unbelievable also to discover that most of the processing is still done manually. In fact, in 2017, CyberSource reported that 79% of North American businesses conduct these reviews manually, which, as you can imagine, takes a lot of time, money, resources, and it would also lack consistency. I guess people doing this cannot be consistent throughout the whole process. So some more facts here. Traditional transactions in 2017, there were more than 1,500 transactions per second by Visa, for instance, and almost 200 billion mobile payments in 2016. So you can imagine the amount of data we are dealing with here. And therefore, this brings us to the actual topic of today, that is the automatic processing, especially to detect illegal activity on the Ethereum blockchain for this topic. But before showing our proposed methods, let us first have a look at what other people tried to do in this respect. And up to the point where we started the study, we could find two related studies where they applied what is known as unsupervised learning to try to extract some patterns from the Ethereum blockchain. But they were more, the first one was more on the transaction level, and the other one was more type of exploratory analysis using graph analysis, just to gain insight from the blockchain. So as far as we know, until the time we started the study, there were no studies that addressed the same question that we are interested in. But I'm aware that since our publication, there have been more activity in this direction. Okay, so here we have the slide about that introduces our work now. This is the research question. Can we automatically detect illicit accounts based on their properties and their activity, their transaction activity? Well, this diagram illustrates the main components in our proposed solution, which I will use to walk you through in the coming slides. So we start by first acquiring a data set of accounts that are already labeled by the community. Then we extract some features from these accounts. We do some cleanup, and then we move on to the machine learning model. And eventually I will share the results that we got. Okay, the first component, accounts. Well, as I said earlier, since as far as we know, we were the first to address this question, we couldn't find any benchmark data set, so we had to build one ourselves. Luckily, there is this Etherscan database from which we could extract existing accounts. And actually, there's a community, the Ethereum community, that already flags accounts that have been found to be illicit. And up to the 17th April 2019, there were 2,179 of such accounts, and we downloaded them all to be part of our dataset. These accounts were flagged as illicit for one of the following reasons. So all in all, they all had problems that made them illicit. Then similarly, we had to also have a list of accounts that were not illicit. So, you know, we have a comparison. We have a description or a set of properties that describe illicit accounts, but similarly, we needed also to describe normal accounts. So there are, as you can imagine, thousands of such accounts, but we wanted to have a roughly balanced data set. So first we downloaded 3,000 accounts, but it turned out that some of them were actually duplicated. So in the end, we only used 2,502 of such accounts. So our data set now consists of around a bit more than 2,000 of illicit accounts and around 2,500 of normal accounts. We also have made this data set publicly available, so other scientists don't need to go through this process all over again, and they will be able also to compare the results using exactly the same data set. Okay, then for each of these more than 4,000 accounts, we wanted to download the transactions, all their transactions. However, there was one limitation. We could only retrieve up to 10,000 transactions from each account, but yeah, we thought this is enough. So we downloaded the latest 10,000 transactions of all these accounts where it was possible. Some accounts had less than 10,000 transactions, and that wasn't a problem. Okay, then the next step was to extract the features. So in our paper, we have the full set of 42 features that we identified. Here we have, I give example of 6 of them. Things like the average time between transactions, for example, the minimum value received, the number of unique accounts with which an account is interacted with, and so forth. So we identified many properties from the accounts, and we extracted all of them from all these accounts that we downloaded. Then we wanted to, have explore the data set by doing some exploratory analysis. And the first thing that comes to mind is to plot your data. But because we have 42 dimensions, this is impossible to plot. So we applied some dimensional reduction technique. You might be familiar maybe with principal component analysis. but another technique which uses non-linear combinations is known as TSNE. And here I have two plots of the reduced dimensions. The first one on the left is showing only 2 dimensions, and the colored data points indicate the classes, the 2 classes that we have, the normal accounts and the illicit accounts. And besides these 3 blobs, red blobs, the other data points overlap heavily with each other. So as you can imagine, it's very difficult to find, to draw a line to be able to distinguish the 2 classes in a very simple way. And on the right, we have, well, the same data, but plotted using 3 dimensions. So here we reduce the 42 dimensions to only 3 dimensions. And again, here we see how much overlap there is between the 2 classes. So it's almost impossible, or impossible even, to find a plane to separate the 2 classes of data. So yeah, this made us realize that this problem is not trivial, and we need a sophisticated machine learning approach to be able to help us with this. Okay, so, well, machine learning is a big field nowadays. It has been growing exponentially in the last few years, and there are many methods that can be investigated. So we had to make a choice, and we decided to go with this, what is known as XGBoost classification model. And I will try to explain it on a conceptual level in the coming slides. So these are the main components of this method. You might be familiar with what is known as a decision tree. So this is the basis function of the XGBoost classification model. Let's see what each of these components are. Well, a decision tree is one of the simplest and yet very effective classification model that is also highly interpretable. This is something that many domain experts prefer to have, rather than having a simple label at the end. You would also like to have why the processing resulted in that label. So here I have a simple example, which I found from the internet, is to determine whether we should do some sports outdoors or not, for example, based on the weather conditions. So you start with the root decision. If it's windy, okay, then you check what the outlook is. If it's overcast, then yes, we can play outdoors. If it's rainy, no. And if it's sunny, we check for humidity, and so forth. So this gives you a hierarchy of decisions until you come to the final decision. Then comes Bootstrap aggregating, or bagging for short. So here what we do is, from the same training set, a training set is a data set that is labeled. So we already know that some accounts are healthy or normal, and others are illicit in our case. Okay. So from the training set, we sample many subsets. And for each subset, we create a decision tree out of them. So we end up, if we sample 10 times, we end up with 10 decision trees. And then finally, the final decision is based on aggregating the decisions by all these classifiers. So this arrangement is usually known, the technical term is ensemble of classifiers. And finally, its aggregation is based on a voting scheme. Okay, another technical term is random forest. This is very similar to bagging, but instead of only sampling a subset randomly from the training set, we also use a random subset of dimensions. Instead of using all the 42 dimensions in our case, you can use 30 dimensions or 20. And every time you change these dimensions for different decision trees. So this was found to be very effective in order to avoid what is known as overfitting. Overfitting means that you have a model that is very good to classify the training data, but then is not very good to classify new data. So the example I usually use with students is that when you are preparing for an exam, you study all the model answers of the past exams by heart, but then you are not able to generalize for a new exam. you cannot generalize your knowledge for new questions. So that's overfitting in machine learning. Okay, the next technical term is boosting. So what happens here with boosting is that, again, here we have a sequence of decision trees or base classifiers, but they are not trained in parallel because they depend on the effectiveness of the previous ones. So let's start with the first one. We train the first decision tree, then we apply some data to it to see how it performs, and then the data points that are wrongly classified will be given more importance to train the next classifier. So there is a weighting scheme involved in boosting. So I'm not sure if you see my pointer. Yeah, I think you see it. So we start with this decision tree, then we evaluate it with some data points, which gives us some output, and that output is used as input to the next decision tree, and so forth. So you can do this for as many times as you want. And then with boosting, we also learn what is known as a weight function associated with each base classifier. So the process is not completely democratic anymore. We do not give equal vote to every classifier, but one classifier may be more important than others. And this is indicated by this alpha parameter over here. Okay, and the last component, well, this is something more technical, gradient boosting. It's based on the gradient descent algorithm, which is used to determine the hyperparameters of the algorithm. But we do not need to go into that technical detail. Okay, so for us, XGBoost, we thought it's a very suitable algorithm for this application at hand. And this is what we apply to our data. Now let's have a look at the results. I think, yeah, what we show with these plots is that the model that we learn is not overfitting. It's quite a technical plot, which is important in machine learning because you need to demonstrate that whatever you're learning is able to generalize for new items as well. But let's go to these results, which are more interesting, I think. So what are we showing here? Well, the most important column is the last one, is the accuracy rate, meaning how many correct guesses our model makes. So this shows that 96% of the time our model makes the correct classification, whether it's an illicit account or a normal account. And the way we did the experiments is using what is known as k-fold cross-validation, meaning that we split our data set into a number of subsets. So in the first one, where we use 3 folds, so we split the data set in 3 subsets, and we use 2 subsets as the training data and 1 subset as the test data. And we iterate by giving the opportunity for each subset to be a test subset. So this is a standard procedure in data science to make sure that your model is not biased towards a certain proportion of your data set. And we did this experiment using different values for k-fold cross-validation from 3 to 10. And what was interesting is that no matter how many folds we use, the results remained consistently around 96%. So this gave us more confidence that our method is indeed very promising for this application. And the other values in the second and the third columns are hyperparameters of the XGBoost algorithm. Okay, so here is what is known as a confusion matrix, which essentially consists of 4 values: the number of true positives, false negatives, and true negatives. Let us try to interpret some of them. For example, if we look at the top left corner, a value of 245, this means that our model predicted 245 to be normal accounts, and indeed they were normal accounts. So they were true positives. And on the bottom right corner, we have 211 as a value, which again is a match between what our model predicted as illicit and what was indeed illicit. And in the off-diagonal, the off-diagonal values 6 and 7 are the true positive, the false positives and the false negatives. So the value 6, the model predicted 6 accounts to be illicit, but in fact they were normal accounts. And in contrast, our model predicted 7 accounts to be normal, but in fact they were illicit. Okay. Now let's have a look at some examples that were classified as false negatives and false positives. Well, these are the addresses in hexadecimal, the identifiers of the accounts that were falsely classified. And we can have a look at a specific account. For example, this account was active for a period of 3 hours in total. Let me see, which account was this? For C115. So this was a false negative. This is the one over here, the first one in the false negative list. So false negative meaning that our model classified it as a normal account, but in fact it was an illicit account. And these are some properties about that account. And here there's another example with some other properties. Okay, let's now have a look at what turned out to be the most important features for our model. Well, here I'm showing only the top 10, I guess, features. So the most important feature turned out to be the time difference between the first and the last transaction in number of minutes. Apparently, illicit accounts tend to have a lifetime much shorter than normal accounts. Usually they are created on purpose for illicit trade. Also, total Ether balance, the minimum value received, and so forth. I think when we look at them, they all somehow make sense to us. Because indeed there is a difference. A person who has illicit intentions opens accounts and trades with smaller values, for example, but with higher frequency, and the account also lives much shorter than a normal account. But a full list of the feature importance is also provided in our paper. Okay, I see I am just in time to conclude this talk. So first of all, what have we learned so far? Well, we have shown that with a state-of-the-art data science pipeline, we have very promising results to identify illicit accounts on the Ethereum blockchain. So we hope that this research will motivate further research in this direction. And we have identified some future directions already. One of them, it's quite natural to see how it performs on other blockchain networks. And we are also interested to see how it can perform on a transaction level. On a transaction level, meaning that even if you have a normal account, maybe only one transaction of that normal account was used for illicit trade. Yeah, we are also interested to see if we can use other features that we haven't looked into yet, and explore other techniques as well. Potential stakeholders. Well, I guess this is the list of stakeholders that we can have: governments, banks who are interested in cryptocurrencies, you name it. I think this concludes my talk for today. yes, I mentioned that our dataset is online. We're using the Dataverse NL repository, which is supported by NWO and KNAW. Yes, that is it. Thank you for your attention, and thanks again to my co-authors, Stephen and Joshua, for their great efforts in this work.
Well, thank you very much, George, for this fascinating talk. You opened a whole new world for, at least for me.